to day 2 Colloquium on recent trends in mathematical sciences. I take this opportunity to welcome and introduce you all to our first speaker for the day, Professor Andrew Vesnin. Professor Vesnin is a corresponding member of the Russian Academy of Sciences since 2008. He obtained his postdoctoral degree and his PhD from Sobolev Institute of Mathematics, Russia. Currently, he is holding the position of Chief Researcher and the head of the Scientific and Educational Mathematical Center at the National Research Tom State University and Chief Researcher at the Sobolev Institute of Mathematics. He is also the leading researcher at the National Research University High School of Economics, as well as a full professor of geometry and topology at the National Research Novosibirsk State University. He is the editor-in-chief of the Siberian Electronic Mathematical Reports and a member of the editorial board of various journals. His research interests include knot theory, hyperbolic geometry, combinatorial group theory, and graph theory and applications. He has more than 100 research papers to his credit, holds the membership of various reputed councils, and is presently the head of the number of research grants, including the grant of the Ministry of Education and Science at the Tom State University. Sir has kindly agreed to give a talk on the topic, knotted objects in three-dimensional space, from mathematical theory to applications. Professor Vesnin, sir, I welcome you and kindly request you to begin with the session.
Thank you very much for a very kind introduction. And it's really my pleasure to give a talk for you. I hope that today's COVID situation in India not so bad, and I hope in future we can meet maybe in life. So today I would like to tell you about big area of topology known as the knot theory, and I will present you some ideas and some results, also some application. Of course, they're related to my personal interests, so I am not able to cover all possible fields today. So as you kindly introduced me, last few years I'm working in Tom State University, and just it's a chance to me to explain where it is. So if you go to the north from India, you will reach Siberia, quite big region, and Tomsk University in this region. So for us, distance to India and distance to Moscow, our capital, is more or less the same. And fortunately, I visited India many times, and I have very nice colleagues, and I really like Indian people. And I know that it's very warm in India now, but here in Tomsk, we have -15 and the snow, so a very big difference. Okay, so I belong to a quite old university. It was the 6th university in Russia. I mean, according to foundation, it was founded by Imperator of Russia. So it was called Tomsk Imperial University. It was founded in 1878. The picture shows you the main building of our university. It's very old, but still very nice building. Okay, and now, oops, sorry. Now let us talk about the objects to study. So what we study in knot theory? Of course, everybody has some naive understanding of what means a knot. First of all, maybe everybody think about rope knots, and you can find many books where you can read about classification of rope knots and some pictures of them, how to manipulate with them, and so on. Another big family of knots you can see when you think about the clothes and especially men's. And also there are some classification of knots according to fashion styles, and the representative of just one of knots, call it the Rinder knot. But of course, it's not mathematical objects yet. Let us go to mathematics. Okay, sorry, just one more example, very famous picture about Alexander the Great, where he cut the Gordian knot. And according to legend about the Gordian knot, mathematical sense, I mean, okay, correctly, in non-mathematical sense, Alexander the Great was the first who solved mathematical problem, but not in mathematical way. I mean, he used a knife. So he deformed non-trivial knot to the unknot, to the trivial knot. And also in generally, when we think about knot, so there are two mathematical problems appear immediately. So can we distinguish this knot from other one, for example, from the unknot? And if we can, so is there any good algorithm to do it? For example, can you do it in polynomial time or maybe in beta? And what is the knot for mathematicians? Of course, we can consider different categories, in topology, perhaps linear, smooth, and just a continuous category. It's, for me, it's no difference now. I mean, just so suppose we look in smooth category, and what is a knot? It's just a circle embedded in three-dimensional space. So in the picture, you see examples of some knot. The first call it unknot, so we call it also trivial knot is unknotted in natural understanding. Second knot is called trefoil. Next is a figure-8 knot. So you see some special kind of knots has names, personal names. It's kind of traditional names, and everybody understand which knot you mean when you use, for example, trefoil. Of course, you can consider embeddings not just one circle, but few circles, and also you consider this object. So you consider embedding of n disjoint circles and call this embedding n component link. And a number of components can be different. If you have only one component, it's exactly the case of the knot. It may be maybe two components, and you see two examples here. One is the Hopf link, where components colored in different colors, and second is the Whitehead link. They're quite famous. They have special names. In this case, due to mathematicians Hopf and Whitehead. Another example presented in the picture is the three-component link. Its link has his special name, Borromean rings, because it was symbol of Borromean family in Italy. So there are many examples, and they look nice, and we defined mathematically, this is just embedding of a circle, and we consider only smooth embedding. Okay. We consider not just a knot, but we consider knots up to some equivalence. So we admit some small deformations in the space. So we consider knots up to ambient isotopy. So all our objects embedded in three-dimensional space, you can smoothly modify. You can use isotopy to go from one object to another. And if you can do it, we say that two knots are equivalent. In the picture presented here, you have two examples of the same knot. On the left, you have a knot which is drawn in trivial way, and on the right, you have the same knot which is drawn in a little bit more non-trivial way. But I think you can imagine that we can deform the right picture to the left one using isotopy of the space. There's no problem to remove this pretzel and to deform from right to left. So we can do it in the picture. Sorry, we can do it as well as the picture. You can do it in three-dimensional space, and we can draw a lot of diagrams, a lot of pictures, but very often we cannot understand if you draw different knots or if it we draw the first. We have some already. So let's discuss two problems. If a given knot is equivalent to the unknot, or if two given knots are equivalent. For example, we have trefoil and unknot. Can we deform one to another one? How to find the deformation, or how to prove that there are no such deformation? And the same question here, we have two different pictures of knots. So who knows? Can you deform one to another or not? How to prove that you can do it? I mean, how to present this deformation, how to find it, or how to prove that this is impossible. And the first idea in this theory is due to people who worked in the end of 19th century. And maybe most famous person in the, most famous person is Johann Benedict Listing, German mathematician, and he wrote his paper in 1847, and you can find in the Wikipedia that he was the first person who introduced the word topology. And he really found something interesting. He introduced some polynomial which related to nodes, and his polynomial was quite nice, but unfortunately it was not invariant. And so about 50 years after the listing, the big group of physicists from Scotland studied nodes, and in particular Peter Tate did it. And he uses the following idea. Okay, let us tabulate of all possible nodes. So after that, we can compare the new node with this tabulated. And he drew a table of nodes up to 10 crossing in projection. So I just recall that in picture you see the trefoil has 3 points in the projection, and the figure node has 4 points in the projection. So he tabulated all that nodes, and looking at tables, he conjectured few statements which known as the Tate conjectures. So in intuitive way, this theory started in 19th century. And up to now, we have still tables of nodes. And this picture show you just initial part. So usually in this theory, people use specific notation. So you see the picture and notation 3 sub 1. It means that this node has 3 crossing, and it's just the first node in this line. I mean, this is property. And if you think about 4 crossings, so also just 1 node, there are 2 nodes with 2 crossings, and so on. So people produces this type of a table in the 19th century, and of course, the people now people can continue this job, this work, and there are many nodes tabulated now, and I just show you the table how the number of nodes grew up. So you have for free crossing just 1 node, but if you think about pictures with 14 crossings, there are about 50,000. And of course, it can be done by computer. You can enumerate them by computer, but always you have the following problem. You can understand if you obtain it is a new one or just equivalent to not, you will already consider it. And there are very interesting historical example from 1885. In this table, there are 2 nodes, which is notation 10, 161 and 10, 162. They were neighbors in table, and people believe they are different nodes. And after 90 years, American mathematician Perker proved that these 2 nodes are equivalent. So you see, you have pictures. These nodes are not too much complicated, just 10 crossings. And people didn't recognize it, they are the same. So if you want to prove that as the same, you need to find some sequence of equivalence transformation from one node to another one. So Perker did it. So I just wanted to emphasize how difficult this problem was. And it's still a problem to distinguish 2 nodes. And if you're interested in tabulations of nodes, so you can find a lot of information in the internet. For generation of nodes, there are 2 very nice sites. First known, not Atlas, and another is Nautilus. It's not just the tables, but also there are database with invariants of these nodes. So totally you can find 98 billions of nodes in this table, up to 23 crossings. okay, you can generate and so on and so on. But if you obtain some nodes, you need to recognize is it a new one or old one. So you have another problem for distinguishing of nodes. Okay. So I want to present you some ideas how people can distinguish nodes by their invariants. It's also a very interesting story. And some invariants can be described very simply, but as usual, such invariant is not strong enough. I would like to explain one very simple invariant, and it's just a invariant. Call it order of the node or minimal crossing number. So you consider all projections of the node on the plane. You just take minimal possible number of crossings. So it's easy to describe, but sometimes it's very difficult to prove this is really a minimal number. So it's just a number. But so imagine this: you have a large amount of possible diagrams, and how you can be sure that you can simplify picture and obtain less number of crossings. And another example of invariant is a little more clever, and it's related to free colorings. So let us define coloring of arcs. So what's the arc? So you have a crossing on the picture. So arc is part from one crossing where you go under up to another crossing where else go under. So for example, the picture of the unknown, there's just one arc because there are no under and upper crossings. And for diagram of trefoil, you see there are 3 arcs. So let us consider coloring of arcs in different color. Let us fix number of colors, let it be 3. And you see that coloring is admissible if all colors are the same around the crossings, or we use all 3 colors. So all colors are the same. You can see that just picture is completely blue. And another example, you have coloring where in each crossing we have all 3 colors. Of course, 2 of them must be the same because we have H coming to this vertex. And let us denote by 3D the number of admissible colors of a diagram. And in this picture, you can see that if you consider unknown, there is only 1 coloring. But if you consider trefoil, you have trivial coloring, but also you have non-trivial coloring. So number of coloring is different. And if you prove that this number is invariant, so we will be able to distinguish trivial knot and trefoil. Oops. And really, Ralph Fox proved this theorem. And he proved that, oops. I'm sorry, just one second. It seems I skipped some slides. Oh, sorry. Let's go a little bit back because I use mouse. It sent me to the wrong slide. Okay, so how we can compare two diagrams of the node? So as we discussed, nodes are objects in 3-dimensional space, but we have only a picture on the plane. So when you draw something on the plane, we show by cutting in the vertex, we show which arc is upper, which is under in the space. So we call such pictures diagram. So from this picture, you can understand which arc of the node is upper, which is in the space. And the German mathematician Kurt Rademeister proves a beautiful theorem, which gives us a way to reduce 3-dimensional problem to 2-dimensional problem. So instead of comparing nodes and links in the space, we can compare diagrams. And he proves that 2 nodes are equivalent if and only if their diagrams are equivalent under Rademeister moves. So if you take a diagram of one node and diagram of another one node, so if you construct a finite sequence of moves where each of them is one of these three types, so you get a equivalent nodes. So these games with diagram correspond to ambient isotopy of nodes in the space. So let's go back to Fox theorem. Oh, sorry, I go in the wrong direction. Sorry. So okay, now we're here. So what Fox did, he used Rademacher theorem. So he proved that if you have some number of coloring free color, some admissible coloring, then under Rademacher moves, you will get the same number of coloring. So you can see it from this example. So first Rademacher move is print of the left. So you use only one color here, and you can use randomized loop to untease this loop. And in the second case, if you have two arcs and you put one over other, so you use it two color before, but you have the third color, you can use it, and again you obtain the admissible coloring. And the third picture demonstrates how it can be if you use a third randomizer move. So considering randomizer move for diagrams, you can prove that this number of admissible coloring in free colors is invariant. And therefore, what we did, we proved that trefoil is not equivalent to unknot. So our coloring is that trefoil is not equivalent to the unknot. So on the way to prove it, we used Rademacher theorem, of course. It's not a trivial statement. And the second coloring, there exists infinite number of knots which are not equivalent to the unknot. So you can consider connect the sum of many copies of trefoil and obtain such examples. And as an exercise, I would like to suggest you to prove that the figure 8 knot admits only one admissible coloring. So it is a picture of the knot, and again you can try to color arcs of the diagram, and please check yourself if you're interested that there are only one coloring. So now let's discuss more complicated invariants, and some of them are very famous. And the third example that I want to discuss is so-called Jones polynomial. It was introduced by beautiful mathematician Logan Jones. Unfortunately, he passed away last year, and he got a Fields Medal for his result. And Jones polynomial became very popular in the middle of 80s, and still now there are many generalizations and many different descriptions of this polynomial. And I would like to mention about another expert in knot theory, Professor Louis Kaufman from Chicago. He found combinatorial approach how to describe Jones polynomial, and I would like to present you some ideas about it. So combinatorial approach is the following idea. So locally you have crossing, and suppose you want to construct some invariant, let's denote it by brackets. So suppose you have some node and consider locally crossing. So you can resolve, or you can change this crossing, you can uncross two arcs, making horizontal line or making two vertical line. And suppose you want to introduce some invariant, which you call just a bracket. It's convenient to use these pictures. And let's suggest the following idea that there are linear relation between the old node and two new nodes, or maybe links. And it's this way give you possibility to decompose any node to collection of trivials. And I would like to show you the picture. Oops. So you can start, for example, from the trefoil and apply this scaling relation to one diagram. You obtain two new diagrams. And again, from these two, you obtain new 4 diagrams, and so on. You have 8 diagrams, and all of each of diagram on the bottom level just a correction of curves on the plane, which does intersect. So there are 2 curves, or 2 or even 3. And how to understand Jones polynomial? So we start with some node. We consider such binary tree of decomposition, and we just think about the way how you write. For example, on H you can see A or A inverse and so on. So you arrive to the bottom, and then you just calculate number of connected components. And this is the way how you can construct. You consider the connected sum of sorry, oops. You can consider the sum of these pictures. I mean, for each picture correspond A in some degree, and plus a number of connected components. And you, from these ingredients, you can construct Jones invariant. I don't want to go to details, but roughly speaking, ideas is like this one. You have a decomposing tree. And how strong is the Jones invariant? So this invariant helps to prove Tate conjectures, which were formulated by physicist Tate in the end of 19th century. Okay, so this invariant quite strong to distinguish knots, but there are examples of 2-component links which Jones polynomials are the same as a trivial 2-component link. This is just an example. If you have this 2-component link and calculate Jones polynomial, you'll get the same polynomial as for trivial link. I mean, both components are trivial and they are unlinked. And also we have examples of infinite family of pairs of non-trivial nodes with the same Jones polynomial. So it's still good, but not enough good invariant to understand nodes. So people still introduce new invariants using different ideas. And also there are mathematical methods coming from algebra. So you can call it the algebraic approach to the node theory. It's based on idea of Artin and Markov. So you can imagine that your nodes are presented as braids. So imagine the cylinder, if your braids go from top to the bottom, and finally you just glue top with the bottom, you obtain something in three-dimensional space. So these braids can be described algebraically. So people, Emil Artin introduced so-called braid groups, and rationalization Markov proved how to solve some algorithmic problem for these groups. For nowadays, people construct algebraic objects as a braid model category. They find some traces of presentations in Hockey algebra using Markov move and so on. There will be a big area of node theory devoted to algebraical methods. Also, you can think about other ideas. Maybe more geometrical. So you can associate a surface with any node. It's called a Cypher surface. So Cypher surface for a node is the following. So you have a surface with a boundary, and the node appears as a boundary of this surface. So you see some examples, and I also hope you can see there is the trefoil, the first example, and the figure 8 node, another example, and so on. So you can use this idea, use Cypher surfaces, and you can use theory of surfaces to understand some more about nodes. So now I would like to tell you something about applications, quite modern application of node theory. And in my discussions, they will be related with molecular nodes. So I recommend you one of nice survey paper, molecular nodes in biology and chemistry. You can see reference here. So people from biology present proteins as three-dimensional objects, and after that, mathematician can recognize nodes or links in these objects. And you see some examples here. So the top line is just proteins, some structures of proteins, and the below line just the line of nodes. And also you see notations 3-1, 4-1, 5-2, and so on. And in these pictures we have carbon and azote. They're not connected. If you connect, you'll get a node. So it's very nice direction now to understand topology of molecular structures. In just one paper, and there are some others. For example, people study DNA. And there's also a very nice paper, 20 years old paper, published in National Academy of Science. And they describe topological challenges in to DNA replication. So you have objects in this space, and you can try to understand what kind of link you obtain. For example, on the picture A, on picture B. And also quite modern methods are used to recognize nodes. And nowadays there are about 3 different approaches. I would like to mention only about one of them. And you can see there is a paper about application of machine learning for node theory. So people also saw the paper described how they used machine learning to obtain to recognize nodes in some proteins. They realized it only for recognizing a trivial node, trefoil for one, and 2 simple another nodes. But this approach is very nice. I mean, if you can, as I told you, it's sometimes very difficult to prove in a strong way that 2 nodes are equivalent or not equivalent, or find transformation to one to another. But sometimes artificial intellect is very helpful. This one is example when you use quite modern theory to a very classical one. And of course, idea of nodes can be extended because of objects which we see in the life. For example, there are quite modern concept of notorious. So we consider a protein is a space, and we have 2 vertices. I mean, terminal vertices denoted here by N and C. So it's azote and carbon. And we can rotate it in the space. And what we know about diagram, we only know the in which point these 2 black balls will be projected. So we don't connect these points in this model, but on the plane. So such object called notorious. And there is very nice paper presented here, very nice report. There are a group of topologists and also a group of experts in biology. For that, one of authors is Andrei Stasik. He is working in Geneva in the biology department. He's a biologist. And people do research in this direction, and I would like to mention you about a very nice database. So it's called NodeProt, so nodes in proteins, and a very big European group, and some others are presented here in the slide. They developed this database of proteins, and for each protein they recognize what kind of nodes or some other large structure appear. And you can find in the internet, just by engine search, this site, there are many interesting information, a lot of examples, and just they describe mathematical methods which they use. They describe which kind of topological invariants used for distinguishing such objects. And only nodes appear in such models, but also some graphs. And it's a very simple kind of graph, just a graph called theta graph. Since it looks similar to the letter theta. So there are 2 vertices and 3 edges. So it's theta graph of proteins, and the same group of physicists and mathematicians, they wrote a preprint about the curves and proteins. If you see a reference, you can also find it online. And we did some research related to knotted graphs, and I would like to mention about our progress. And the object which we study is the knotted graph in three-dimensional space. So you have not just embedding of a circle, but you have graph, and after that we embed this graph. And in these pictures, there are two vertices. Usually, this very simple picture. There are usually two vertices, and this theta is three edges. So it's theta graph in both notations. So you see different kind of embedding. And similar to John's polynomial, there are also nice invariant introduced by Yamada, Japanese mathematician Yamada, and he suggested this invariant. And with my colleagues, we investigated the behavior of this invariant under some transformation of graphs with colleagues with China. And in this slide, you see the initial list of theta graphs. Also, they are tabulated and they have some standard notation similar to knots. So it's the trivial one and more complicated and so on and so on from these 14 theta graphs. And there is table of their Yamada polynomials. So it's kind of Laurent polynomial. So it's positive and negative degree in variable A. So if you don't know how to distinguish knots from this picture, you can calculate Yamada polynomial and just check that all these polynomials are different. Of course, it can be done for any theta graph, but also you can consider more complicated graphs. And we also studied properties of this Yamada polynomial for graphs in mathematical sense. So we prove the truths of Yamada polynomials are dense in the complex plane. This kind of approximation theory, approximation methods used. And our next step is the proteins in virtual knots. Sometimes we have a picture and have projections of different planes, and we don't know what is correct, what is not correct. So to apply knot theory, you want to connect the ends, but it can be done in different ways. For example, for these three projections, you can add the dotted line. You can send it over the crossings or under the crossing, or just you don't know over or under. In this case, we introduce so-called virtual crossing. So we don't specify which kind of crossings there appear. We just kind of some virtual, so unclear crossings. And also in this case, theory can be constructed, and it's called the theory of virtual knots and rings. And similar to Rademacher's theorem, there are theorem which means to construct invariants. We can reduce the problem in dimension 3 to problem in dimension 2. You just compare diagrams. And with my colleagues with India, from Europa, from it's, I suppose you know it is not far from Chandigarh, from Punjab. We introduced new invariants for virtual knots. And this is just initial list of virtual knots, just give you an idea how they look. There are some usual crossings, some virtual crossings. And we used some smoothing crossings, maybe not necessary to go details, and we defined some diagram with labels for a diagram of virtual node. Like here on the left, you have virtual node, on the right, you have some labeling. And using this labeling, we define so-called L polynomial. So you take sum over all classical crossings, and you have two variables, T and L. So sign plus is just plus or minus, and the index and this number depend of crossing. And we prove this polynomial is invariant on virtual node. And nowadays we developed this theory, and last month we put in archive our new preprint where we extended as far as possible this idea. I mean, we introduced new invariants which is stronger, but also using the same idea as the Jones. So we decompose, and after that we take sum for different states. Okay, I think my time is almost over. So at the end, I just suggest you some books or paper or journals. So in knot theory, we have special journal called Journal of Knot Theory and Ramifications. There are about 12 issues each year. So there are a lot of papers, a lot of people working in this theory. And you see one of the person about whom I mentioned is Louis Kaufman. He's the founder and editor-in-chief of the journal. And also there are many books. There are a special series of books called Notes and Everything, published to the World Scientific, and you can find some pictures of book here, but really there are, I don't know, maybe about 30 books already published, and they devote to different aspects of the knot theory, knots in physics, on quantum topology, on history and science of knots, and Gauge field knots and grades as ideal knots, ideal in sense of biology. So I hope it's that you will find this theory interesting. It's a big part of low dimensional topology, but it's used methods and ideas from a very big collection of nearest areas of mathematics, so in group theory, in ring theory, in the theory of surfaces for integrable systems, and so on and so on and so on. And I stop with these books, and thank you very much for your attention. And if you have some questions, you can ask now. You can send me email, and you can discuss more about knot theory, which is my major area. Thank you very much for your attention.
Thank you, Professor Vesnin, for an enlightening session. Participants who have any query can put forward your queries to Sir at the mentioned email ID. Because of time restrictions, we will not be able to take the questions right now. Thank you, Sir, for discussing such interesting applications like knotting of proteins and discussing your recent research with the audience. I'm sure the participants must have enjoyed and learned from the information shared by you. Thank you.
Oh, you are welcome.
Pleasure having you here.
Be free to write me. Thank you very much.
Thank you. Moving forward to the next session for the day. It is my pleasure to introduce our next speaker, Dr. Phon Sriam. Dr. Phon Sriam has done his PhD in mathematics from the Pennsylvania State University. He is currently an associate professor at the Department of Mathematics, Silpakorn University, Thailand. He is the recipient of about 11 awards, including Paul Brockman Prize from the Fibonacci Association, Distinguished Researcher Award, as well as Silpakorn Innovation Award. He has over 50 publications and has published a book entitled Introduction to Analytic Number Theory just last year. He has been a reviewer for Mathematical Reviews of Math Science Net since 2013 and is a referee of about 13 journals, including the American Mathematical Monthly, the Fibonacci Quarterly, and Hardy and Ramanujan journals. His main interest is in number theory and is currently working on various topics, including the problems concerning BT sequences, long arithmetic progressions, palindromes, and Fibonacci coefficients. The topic for his talk today is some recent problems on arithmetic progressions and palindromes. Sir?
Yes.
Dr. Phon Sriam? Yeah.
Yes.
I welcome you and I request you to kindly begin with the session.
Okay, thank you.
Thank you.
Can you see my screen?
No, sir, not yet.
Oh, okay. Can you see it?
No, sir.
Oh, let me try again. I think I have to change my device. This doesn't work. Sorry.
Okay, sure, sir.
Recording in progress.
I think you've joined with another device as well.
Hi. Okay, so I think I can share the screen now, right? Can you
Yes,
see
sir.
my screen? Okay.
Yes.
Okay. Okay, does it work?
Yes, sir.
Okay, so let me close another device. Sorry for the delay. Okay. Okay, so can I begin? Hello?
Yes, sir, you may begin.
Okay, so today I would like to talk about arithmetic progressions and palindromes. So sorry for the delay. So let me start with this. So I will divide the talk into 3 parts. So the first part is about reduced residues, and the second part is palindromes. And if I have some time left, I will say something about other problems in palindromes in the third part. So first, let me recall some well-known results from the primes. So when we speak about primes in arithmetic progressions, we usually think of Dirichlet theorem or prime number theorem for arithmetic progressions. A simple form of this says that if you have a reduced residue class, then there are infinitely many primes in that reduced residue class. And this is like a dual of the other, the Dirichlet theorem, the Green-Tau theorem, which again in a simple form says that the sequence of primes contain arbitrarily long arithmetic progressions. So it is like the problems in primes are solved. So what about other integer sequence? So you can pick any sequence of your interest. So suppose that, let me use this. Okay, suppose we have an, which is a given integer sequence of your interest. So you can ask the following questions. So the first question is like this, but you change from primes to your integer sequence. So you can ask, suppose the residue class are given, and are there infinitely many n such that the terms in your sequence is in this residue class. So, this is number 2. Sorry, this is just mistyped, typographical error. So this is number 2. This is like Green-Town theorem, but not for primes, for your integer sequence. So you can ask if your integer sequence contains, suppose it contains a limited progression of length L. Can you determine an upper bound of L? Or maybe what is the maximum value of L? So in the case of primes, the answer is depend on the residue class. If this is a reduced residues, then the answer is yes. And if this is not a reduced residue, then the answer is no. And in number 2, when this is the sequence of primes, then the maximum value of L is infinity. I mean, L can be any positive integers. So L diverges to infinity. So in my cases, because primes are already solved, so I change to something which is easier to calculate. But I expect that because it is easier to calculate, I should have more precise answers. So in my case, I consider a reduced residues system. So this is just to recall the definition of reduced residues. So the reduced residue modulo n is any integer which is relatively prime to n. And reduced residue system is the set of integers which are relatively prime to n, and any integer is congruent to exactly one of them. And the least positive reduced residue system modulo n is the set of positive integers from 1 to n, which are co-prime to n. And I will write the set of least positive residues by this symbol an. So this is just example. So just to recall the definition, in case you forget, suppose n is 10. So if you look at the number of integers from the integers from 1 to 10, and you pick only the one that are co-prime to 10, which are 1, 3, 7, 9. So these are the reduced residues modulo 10. And again, this is a Euler function. So there are 4. So phi of 10 is 4. And when n is large, you can use this formula. For example, if n is 100, then phi of 100 is this number. So next, I'm going to talk about some unsolved problems which is in this book. It's like a famous book in number theory. So everyone in number theory knows about this book. And so this is from section B40 of Richard Guy's Unsolved Problems book. The name of that section is Gaps Between Totatives. Totatives is the same as the set of least positive residues, which I just recall. So here, this is the set of our reduced residue modulo n, and Erdős conjecture that this sum is less than n squared over phi n. This is like big O notation. Okay, so when I write fx is big O gx, or fx less than gx, it means this. And there are some, I think there are many people who try to solve this conjecture, and this is just some of them. So Hooley in 1963 showed that the sum. Okay, but not this is square. But Hooley can prove that if it is not square, if alpha is less than 2, then the answer is correct. So if you can just plug in 2 here, then it will be the same as Erdős conjecture. But this is just partial answer because Hooley proved it for less than 2. And if we put 2 in here and then he calculate, it doesn't give the answer to this problem, just almost, because this is a little bit larger than Erdős conjecture. And then Phon proved it on average, and then Montgomery and Phon completely solved Erdős conjecture. So one of the problems in this section is solved in 1986. There are more than one. Okay, so another problem is by Bernoulli-Recommend. He asks if the set of least positive residues contains long arithmetic progressions for large n. So suppose for each n, I let Fn to be the length of the longest arithmetic progressions in the set of least positive residues modulo n. So the question of Bernoulli-Recommend is that whether or not Fn diverges to infinity. So again, let's see some example. Suppose n is 9. So the set of least positive residues modulo 9 is 1, 2, 4, 5, 7, 8. And we look, we consider the arithmetic progression in this set. So 147 here is an arithmetic progressions, and another one is 258. Okay, which has length 3. There are 3 elements in here. So this is a arithmetic progression of length 3. And after you try for some time, this is just finite set. So you can just try, and then you can see that there is no length for arithmetic progressions. So which means that in this case, the length of the longest one is 3, because there are 3. This is 3 terms arithmetic progression, and there are no 4 term arithmetic progressions. So the answer for this case is 3. So f of 9 is 3. And this is some values of Fn when n is small. For example, this, this is, so the longest one is here, okay, when n is 7. Because when n is 7, the real residues modulo 7 is 1, 2, 3, 4, 5, 6. So you can choose 1, 2, 3, 4, 5, 6 to be your arithmetic progression, which has length 6. Anyway, if you change the reduced residue class, for example, when n is 10, n is 1, 3, 7, 9, and you can see that you can have 2 terms arithmetic progressions, but you can not have 3 terms arithmetic progression in this set. So Fn is 2. But if you change to other residue classes, for example, this one is also a reduced residue system modulo 10, and it contains arithmetic progression of length 4, which is this. This is 4 terms arithmetic progressions. So it is natural to extend the idea of Bernoulli-Recommend, extend his questions and consider all residue classes. So suppose Bn is any reduced residue system, and Fbn is the length of longest arithmetic progression in this Bn. And we consider this function, which is the maximum value of or fbn when B is any reduced residue system modulo n. So the original question of recommend just asked about Fn, not this F, the original one, whether or not it diverges to infinity. So about 22 years later, Stump obtained this lower bound for Fn, and from this lower bound he can prove that Fn diverges to infinity, like this. Okay. Anyway, in analytic number theory, we just don't stop here. We don't just want to know that it diverges to infinity. Very often we want to know more. For example, how fast Fn diverges to infinity. Or in my cases, I want something like asymmetric formula or exact formula for Fn and capital F too. So here is my answer. So just about 1 year later, I got an idea to calculate the exact formula for Fn. So suppose n is square free, the formula is look like this. I will give this slide to the organizer, so you can look at it later. So let me just say that I have the exact formula for square free of n, and I also have the formula when n is not square free, which looks like this. And for the capital F, the maximum of all longest length in any residue class, the formula is simpler. It's just like this. Okay, and I also calculate the maximum and minimum order of Fn, both F, and the maximum order of yes, here. The maximum order of both functions are n, and the minimum order is log n. So how fast is diverges to infinity is the answer is here. So when it goes slow, it go like log n, and if it go fast, it go like n. So that's all for part 1. I have 3 parts, so I may go a little bit quick, and also lose some time in the beginning because my device doesn't work. Sorry about that. Should I go on part 2, or if you have any question on part 1? Okay, let me just go to all of this, and then if you have questions, then you can ask at the end of my talk. So part 2 is about elliptic progression of palindromes. So let me recall again the definition of palindromes. A positive integer n is a palindrome if the decimal representation of n reads the same backward as forward. You can look at other types of integers called palindrome in base B or B-adic palindromes. So it is the integer which has the palindromic representation like this. Okay, so when you write n in base B, and then you look at the representation, it has symmetric properties. So this one is equal, this one is equal like this. Okay, ak minus I is equal to ai for every I. So this is some examples. So this is palindrome in base 10. If I don't specify the base, is always in base 10 as usual. So this is in base 10. So when you read from left to right, it's 1 to 1. From right to left is 1 to 1. So this is palindrome. And this is the number in base 5. And 1, 2, 3, 4, 3, 2, 1, and 1, 2, 3, 4, 3, 2, 1 are the same. So this is palindrome. And suppose we look at 9. you can write 9 in base 2 like this and base 3 like this. So which means that 9 is a palindrome in base 10 and base 2, but not in base 3. Again, you can look at this slide later. So I will just say that our palindromes may be considered like application mathematics, but it is also research mathematics. There are many articles about palindromes already in the literature. So this is some examples. Again, some examples, reference. Okay, let's come back to arithmetic progression. So in 1998, Ami and Sotak showed that if A and D are positive integers, and at least one of them is not divisible by 10, then there are infinitely many palindromes in the arithmetic progression A mod D. So this is like you change from this theorem to palindrome. So this palindrome in arithmetic progressions. So the do of this problem is to consider of is the consideration of arithmetic progression of palindromes. So Domotov asks on Math Overflow. This is like a website of mathematics. You can search in Google. So Domotov posts a question in this website, Math Overflow, whether the sequence of palindromes contains long arithmetic progressions. And then Turlitown gave a negative answer to this question. And from his comments, it should be the length should be less than 10 to the 8. So this some picture. I took some picture from that website. Okay, so this is the question. Okay, and the user is here, Domotov, and so this is the question that Terence Tao give in the website. Here is the picture of him, and this is what I said. Okay, that approximately he thinks that the length should be less than 10 to the 8. The length of the arithmetic progression of palindromes. So is this negative answer because Domotov asks if it contains arbitrarily long arithmetic progression of palindromes, but not long. It should be less than 10 to the 8. I am also interested in this kind of question, so I solved it in just last year. So actually, it's not 10 to the 8. I mean, 10 to the 8 is correct, but it is not sharp. So actually, the arithmetic progression of palindromes have length at most 10, just 10. And 10 is sharp because you can find infinitely many progression of palindromes which have length 10. And you can change the question a little bit. You don't have to look at a palindrome is in base 10. Maybe you can ask yourself what is the longest length of elliptic progression of B-adic palindromes. I mean, I saw just the case B is 10, but you can solve the general case. I think the method in my papers can be adjusted somehow to prove this kind of result for any B, or at least when B is larger than 10 or something like that. And you can also extend it to generalized B-adic palindromes where you allow 0 in front of the digits. Okay. I have time. I think I have 15 more minutes. or maybe
Yes, sir.
10.
Yes,
10,
sir.
right? Yeah, okay.
15 minutes.
Okay. So let me talk about part 3 a little bit. So again, this is about palindromes. Continue from part 2. This is one example. In 2016, Banks proved that every positive integer is the sum of at most 49 palindromes in base 10. Okay, just 10 edit. And then just 2 years later, Seller, Luello, if I read correctly, Luca and Baxter extend Banks' result in 2016. They proved that it doesn't have to be 10 edit palindromes. You can prove it for any base as long as it is larger or equal to 5. And the summand is also reduced to 3. Okay, so every positive integer is the sum at most 3 periodic palindrome for any fixed p larger than or equal to 5. So there is a small problem left because usually we consider b from 2. So there are 2, 3, and 4 to be considered. And this is done in the same year by, again, if I read correctly, Rajasekharan, I think, Rajasekharan, Chalice, and Smith proved the remaining case. So when b is 3 or 4, then every positive integer is the sum of at most 3 periodic palindromes. And if b is 2, then you need 4 summands to write the positive integer as the sum of these palindromes. This is just example. Okay, so suppose I consider is base 10, and then I can write 720 as a sum of 3 palindromes. Also, these are palindromes in base 10, and I can also write it in base 2 like this. This is 720 in base 2, and this is not palindrome, but it can be written as a sum of palindrome. In here, I use just 2. Again, this is just another example. Okay, that about additive property of palindromes, and which is already complete because they have done everything. Right. Another problem again comes from math overflow or math stack exchange somewhere, one of the two of these 2 websites. Someone want to know about the number of palindrome in each base. So here, this is the work of my student and I. We calculate the number of palindromes up to m. How many? I mean, so suppose b is positive integer larger than or equal to 2, and m is any positive integer. And suppose m can be written as this in base b. Then we can count the number of all palindrome less than m. And the formula is like this. So this is again some examples. For example, if I want to count a palindrome less than 100, I can count directly like this. There are 18 numbers which are palindromes, but this is just the general formula when m is any number. If you plug in m equal to 100 here, you will get the same number 18 here in this formula. Okay, so I know the exact formula for the number of palindromes, but the formula, you can see it looks complicated. I still cannot answer which base contains more palindromes. I mean, the original question asks, for example, if you consider palindrome in base 2 and palindrome in base 10, which base contains more palindrome? From this formula, it's not obvious. So you have to somehow analyze more there are two ways to compare the number of palindromes. There are infinite. So to compare them is not compare like infinite or finite. They are both infinite, but there are many kinds of infinite. In analytic number theory, we can use like big O or little o notation to compare the size, or you can use maximum order or minimal order to compare the size of infinite. So one thing that I assign my student to do is to calculate the reciprocal sum of all palindromes, and these are our sorry. So I let SB to be the sum. The reciprocal sum of all B-adic palindromes. Okay, and I want to compare the size of SB for each different B's. Okay, first of all, in 1980, Charlotte, the same Charlotte as before, one of the authors who proved that every positive integer is the sum of at most 3 B-adic palindromes when B is 3 or 4, and at most 4 2-adic palindromes, the same Charlotte. In 1980, he proposed this problem. The reciprocal sum of all B-adic palindrome converges, and this problem was solved by Clauser, maybe just 1 year later. So it is convergent, but what is its value? And here is some lower bound and upper bound that my student calculate. So for example, when B is 2, this is the lower bound for the reciprocal sum of 2-adic palindromes. And this is the upper bound for the reciprocal sum of all 2-adic palindromes. And then go on. This is 10. So 10 is like palindromes that you know. Okay. And lower bound of the reciprocal sum of all palindromes in base 10 is this, and this is upper bound. And the error is not exceeding 10 to the negative 8. So this is very close. You can see this is very close, 337, 237, and you know the difference will be somewhere very far. Okay, so first of all, the sequence SB is still increasing. So from this point, we can say that when we look at the reciprocal sum of 2-adic palindromes, palindrome in base 2 and palindrome in base 10, the reciprocal sum of base 10 is larger than the reciprocal sum of base 2 palindromes. So this looks like we have more palindromes in base 10, but this is not a counting measure. This is like reciprocal sum is like logarithmic measure. So in logarithmic measure, we have more palindrome in base 10, more 10-adic palindrome than 2-adic palindromes. And we also calculate the asymmetric formula for SB. It looks like this. So for any B, the reciprocal sum of all B-adic palindromes is approximately log B plus gamma plus ... and this is the error term, O star 6 log B OB to the 3. And this estimate is sharp because you can replace O star by omega plus. Okay, let's come back to the original questions. So suppose that ABX is the number of B-adic palindromes less than or equal to X. So the original question is like this. The number of 2-adic palindrome less than X, and this is the number of palindrome in base 10 which are less than X. Which one is larger? This is the original question, and maybe X may be like very large. or maybe in general, suppose B and B prime is different base. Can we compare the number of polynomial in base B and B prime? And this is the answer. I just answered this year. So recent problems. So this should be recent because this is this year. So suppose B and B1. Wait. Sorry, there is no B2 here. Sorry, just B and B1. Positive integer larger than 1. So this should be 2. Sorry. So B larger than B1 and B1 larger than or equal to 2. The answer is that actually we cannot compare it. The number of polynomial in base B and minus the number of polynomial in base B1 has infinitely many size changes. So more precisely, sometimes the small base has more palindromes, and sometimes the larger base has more palindromes, and there are infinitely many of them. Okay, my last slide. Thanks to our organizers of this conference for inviting me to give a talk. And this is some of my reference. Thank you for listening. That's all.
Thank you, sir, for such an informative session, for sharing your insights on something as interesting as the arithmetic progressions. It was a pleasure having you here with us today, sir. Thank you.
Thank you. Thank you.
I now request Dr. Pooja to welcome our next speaker for the day.
Thank you, Dr. Karuna. Now I take this opportunity to welcome our speaker for this session, Dr. Mansaf Alam. Dr. Mansaf Alam has been working as an associate professor in the Department of Computer Science, Faculty of Natural Sciences, Jamia Millia Islamia, New Delhi. Young Faculty Research Fellow, Editor-in-Chief in the Journal of Applied Information Science. He has published several research articles in many reputed international journals. His area of interest includes big data analytics, machine learning and deep learning, cloud database management system, object-oriented database system, genetic programming, big informatics, image processing, image retrieval, and data mining. He serves as a reviewer of various journals of international repute like Information Science. He is also a member of program committee of various reputed international conferences. He is in editorial board of some reputed international journal of computer science. I humbly welcome you, sir, and invite you to speak on the topic, Big Data, IoT, and Cloud Computing Application in Real Life.
Thank you very much, ma'am. Respected principal, faculty members, and my dear participants, good afternoon to all of you. It is my pleasure to give a talk in your great conference and great institution. Dear participants, you know, these days technologies play an important role in our society. In our society, we are facing a lot of problems, and scientists come forward to help the society with the help of technology development. And mathematics play an important role in technology development. Technology can't be developed without the mathematics. So friend, today I'll discuss on a recent topic used by the scientists to help the society. In our society, we are facing a lot of problems. Right now, emerging technologies are big data, cloud computing, IoT, artificial intelligence, and the blockchain. These 5 technologies are frequently used by the scientist, by the researcher to develop new application to help the people in the society. And mathematics play very important role here. Ma'am, can you give me permission to share my slide?
Sir, already permitted.
Permitted. Okay. Thank you, ma'am. Thank you very much. So, friend, let us see here. AI-based big data analytics big data analytics using, my slide is visible or not? Just a minute. Okay. So we have to use the technology, IoT, cloud computing to solve the real life problems. Friend, we are facing a lot of problems in the society, and artificial intelligence is going to help the people. So big data play the important role. We are using the concept of artificial intelligence. What is going on? Slide. Just a minute. So AI-based big data analytics using IoT cloud environment. Let us see the human face of big data. We can say our brain is stored the big data, process the big data, but how these all data are managed in the human mind. And we scientists inspired from this and implement the same thing in doing the data analytics. There are 4 take place in our mind, video story in our mind from nursery to PG and the PhD. How that data are managed. And I'll just show the implementation. First step that take place is known as the attention. As we know, there are several input-output devices in computer by which you are giving the input processing the data and getting the output. In human being, there are several input-output organs. So through input organs, we are getting the data and storing in our mind. First, you have to among your surrounding. If network is established, the listener is receiving and you are transmitting. Listener are asking question, you are receiving and you are processing. So after attention, you are getting data to your mind, and then the second step start from there. That is rehearsal. That means you are going to refine the data, whether the data got by you is quality data or not. So you will ask question again and again to refine the data to make the quality data, because you have to take the decision on that quality data. Three types of questions arise in your mind. First question, what? If question what is arises in your mind, that means you are a student. If two questions arises in your mind, what and how, then you are a teacher. And three questions at a time, what, how, and why, then you are a researcher or a scientist. After refining, making the quality data, another process starts in your mind that is known as the encoding process. Encoding process to transfer the data from short-term memory to long-term memory, and in long-term memory, your data are stored in the form of a frame. And fourth step, that is known as the retrieval. As soon as you get information from the surrounding, if any question you got from the surrounding, you search the answer of that question in long-term memory and respond accordingly with the output organs. These are the 4 steps take place. Now see, these 4 steps we are going to give to the machine to make the machine a strong, intelligent, behave like a human being. We are teaching a student. That means we are giving information to the student, and a student can store that information in her or vision of the course. You are taking the test because you want to check whether I have delivered the message, given message information to the student, have completely learned or not. So he and she appear in the examinations, and there, if she pass, then you grant a degree. That is okay. Similarly, we are going to give the training to the machine, to the device that take the decision automatically. So let us see, artificial intelligence play important role here in decision making, because you are going to train the machine, that machine can take the decision. Now look at the artificial intelligence popularity in the world. How much this artificial intelligence is popular in the society. That AI divided in 3 parts. First one, 2 days, going on, and under developing, and what would be the future. A questions asked, do understand what artificial intelligence is? 72% people answered yes, we are aware about the artificial intelligence. 17% no, no idea about the artificial intelligence, and 11% not sure. Now you know what is the capabilities of artificial intelligence, what artificial intelligence can do. See in the green color, that is in the existing right now. 57% ability to learn, 50% solve problem, 37% interpret a speech, 35% ability to replicate human interaction, 51% think logically, and undergoing 19% play game, 18% run on surveillance, 31% replace the human job. So this is great problems we have to face in our society. After implementations of artificial intelligence, many jobs will be replaced with intelligent machine. So there will be a crisis in the society. We have to think over it and see in future what will happen. 10%, see the blue color, indicate the future of artificial intelligence. What can you do with the help of artificial intelligence? 10% take over the world. 8% control your mind. Think what will happen if someone is going to control your mind. There will be a major problem. Anyone can control the mind of any other people. And you can also give the machine can feel and the emotion same as the human being. So this is the capabilities of artificial intelligence, and people are using this concept in day-to-day life applications. See, I told you there are 4 steps take place in your mind. Similarly, when we are going to do the data analytics, again we are using here the same 4 steps. First one, data generated. I told you attention to get the data in your mind. Similarly here, first data generated, and data may be a structure, unstructured, video, text, etc. So that data is just stored somewhere else, or you can get the data with the help of IoT devices. And friend, you know what is IoT? Internet of Things. And we can say IoT is a source of data. You can connect each and every object in the society with the internet. For an example, table, chair, fan, all objects at your home will be connected with the internet. So think what amount of data will be generated. Sometimes you want to shift your bed from one room to another room. Some manpower is required. But with the help of IoT devices, only set the locations and that bed will be shifted from one room to another room, one location to another location. Think what technology play here. And this technology into the existence. You are controlling your AC from your office. You're going to switch off bulb, all appliances of your home with the help of mobile phone. There the IoT technology is used. You are using the smart home, a smart door. You can close your door from the remote locations. You can open the door, you can close the door. There the concept of IoT is used. So now we can say IoT is a source of data and the huge amount of data is generated. So big data is a problem. To store the data, a concept of cloud computing is required. So cloud computing is the solution. And we all people are using the concepts of cloud computing. You know, everyone are using the WhatsApp, that is the cloud. We are using the Zoom platform, that is also the cloud. We are using the Google Meet, it's also the cloud. We are using the Google Drive, Dropbox. Many people are not aware about this concept. They are only using it, but that all are the cloud. Gmail, all are the cloud. So cloud computing are solving our real life problem. See, these all technology work all together to solve the real life problem. Let us see once the data is generated, and then you have to store it. You can store that data in the database or the server, as I told you, after getting the input organs and data and storing the brain. And you have to process before storing the data. You had processed the data, but here after storage, you are going to process the data. That is the data processing. You can process that data with the help of CPU or a GPU. And then you have to use the artificial intelligence algorithm to detect the pattern. And the fourth step, actionable insight, means the predictive signals are generated. Same 4 steps are used here in the real life to train the machine, to make the machine intelligent. Now see, artificial intelligence is the oldest concept, but most frequently right now people are using. And 2 concepts are more popular right now: machine learning and the deep learning. Machine learning and deep learning are the subset of artificial intelligence. And deep learning is a subset of machine learning. And we are going to train the machine with the help of machine learning algorithm to make the machine intelligent. Data analytics is not possible without the data. Making machine intelligent is not possible without the data. If you don't have a data, you can't train the machine. If you don't have a teacher, you can't train the student in your college. To make the successful AI-based machine, data play important role. If you have a data, you can train the machine. If you don't have a data, you can't train the machine. Now see what is going on in the real world in 1 minute. I'm going to show you the survey from 2016 to 2020. In 1 minute, how much data is generated? Everyone are using the WhatsApp. In 2016, 20.8 million messages sent every minute. But what happened after 1 year, in 2017, 29.2 million messages sent, means 9.2 billion messages increased in 1 minute. In the case of YouTube, 2.78 billion video views every minute. In 1 minute, 60 seconds, 2.78 million video views. So you can calculate in 1 hour, 1 day, 1 month, how much data is generated right now. If you talk about the Google, in 2016, 2.4 million search queried every minute, and in 2017, 4.1 million video views. The YouTube users increase, the view of YouTube become the double. 2.78 to approximately 4.1 means approximately double. In the case of Facebook, 701,389 in 2016 and 854,166 in almost all social media, on all social media platform, data increased day by day. Now see what is the scenario of 2018 and 17. Now the YouTube data that become the 4.3 means the growth rate of YouTube data now increase slowly from 16 to 17 just double, but from 17 to 18 only 0.2% increase in the data. Similarly, see in the case of Google, 3.5 million search query in 17 and now 3.7 million search query. Here also 0.3, 0.2 million of 2019 and 2020. YouTube now 4.5 million in 2019 and 2020. In 2019 was 3.8, but in 2020 is 4.1. So day by day, data is increasing in our society. That's why a very important role to train the machine, to implement the concept of artificial intelligence. If you have enough data, then you can make the machine enough intelligent. Just a human being data that is known as the knowledge, then they can take the right decision, good decision. Similarly, if you are giving the more knowledge, information to the machine, so machine can also behave like a human being and think logically as a human being think. Huge amount of data generated in the real world. That's why a separate discipline open, that discipline known as the data science. And in data science, mathematics play important role. Business play important role. So data science, three disciplines can work together: mathematics, business, and the computer science. Three discipline people work together in the field of data science. And most of the many universities have started the course of data science, and the coming future, maybe a department will be open, but in USA, in Europe, in UK, I had visited several times, and many years ago, they started master in data science. It's a very important discipline. Let us see one more data. How many devices are connected in the real world? See, in the 1990, 0.3 billion devices were connected. In 1999, 90.0 billion connected. 2010 was the 5.0 billion. 2013, 9.0 and 2020, that was 20.1.0 trillion devices will be connected. So just imagine how much data will be generated. So new technology required to store the data. Even the cloud technology is very important. So you have seen there is a cloud concept on your mobile phone, tablet, tab, Google Drive, and all data is stored on the drive. Even your device burnt, damaged, but your data will not be damaged. If you bring a new devices, your all data will come automatically on your device. So cloud computing play important role in the safety and security of your data. So if your data is on a cloud, that is totally secure. Anytime, maybe fire in your house, your device is burnt, any disaster, your device is damaged, but your data will not be lost. Once you bring the new device, you can get the all data. Now see one scenario of the world, how much data generated in North America, greater than 3,500 petabyte data. In Europe, greater than 2,000. In China, greater than 250 petabyte. In Japan, greater than 400. In Middle East, greater than 200. And in India, greater than 50 petabyte data generated. So you know the definition of data in a high volume, variety, people to people communications, people to machine communication, machine to machine communications. Machine to machine communications means two machines are talking to each other, they are transmitting the data, they are talking to each other. And we are also talking to the machine. And people are talking people to people. So people to people means virtual communities, social networks, weblogs. That is known as the people to people communications. People to machine communications, medical devices, digital TV, e-commerce that come under the people to machine, and machine to machine communications, sensors, GPS devices, and barcode scanners. So these all are the various sources of data, and the huge amount of data are generated in the real world. So a separate discipline is also required. Now, friend, see what are the various type of big data analytics. First one, descriptive. Second one, diagnostic. Third one, predictive. And fourth one, prescriptive. If you have a problem, now you have to take a decision what type of big data analytics required to solve your problem. To get the answer, you can take the decision. Just what happened, if you want to get the answer of what happened, that means you have to use the descriptive data analytics. And level of advancement of descriptive data analytics is low. And incorporations of AI and machine learning is not usually the level of popularity is used almost all organizations. Another type of big data analytics that is known as the diagnostic. Then you can ask a question, why did it happen? And if you want answer of it, then you have to use the diagnostic big data analytics. And the level of advancement of this is medium, incorporations of AI machine learning sometimes, and level of popularity used by many organizations. And the third type of big data analytics, that is the predictive. You can ask a question, what will happen next? If you get the answer, that means you have to use the predictive data analytics. Level of advancement is high. Incorporations of AI and machine learning are usually, and this is used by a smaller but growing group of a company. And fourth one, that is the last one, prescriptive big data analytics. If you ask a question, what should I do? If you want to get the answer of it, then you have to use the prescriptive big data analytics. And the level of advancements of this one is very high. And incorporations of AI and the machine learning is always, and the level of popularity of this one is not yet widespread. So friend, these all are the various types of big data analytics. And due to the limited time, I think my time is expired, 3:30 to 4. So without delay, just within 2 and 3 minutes, I will finish because I have allotted the time only 30 minutes. So big data analytics for the cost reductions, fast decision making, and new product and the services. So friend, now I am going to stop here because I have no enough time to discuss more things. So now this platform is open for you people to ask any question in your mind. If you have any question in your mind, feel free to ask the question.
Thank you so much, sir, for this informative session and enlightening us with the application of big data IoT and cloud computing in real life. Thank you so much, sir. It's a pleasure having you.
Thank you, ma'am. Thank you very much.
Next, I would like to extend a warm welcome to our next speaker for the session, Dr. Stefano Innamorati. Dr. Stefano Innamorati, he is an associate professor of geometry at Department of Industrial and Information Engineering and Economics, University of L'Aquila, Italy. He is a referee for the Journal of Combinatorial Designs. He is a member of INDAM Group's National Group for Algebraic and Geometric Structure and their application. He has various research papers to his credit. His research interest has focused upon one specific topic, characterization and classification of remarkable figures by intersection number in finite projective spaces. He has been the owner and coordinator of national research projects and collaborators of international projects. He is the author of publication reported on widely circulated international journal in this sector. His topic for today's talk is combinatorial characterization of some finite algebraic varieties. I welcome you, sir. It's a pleasure having you with us today.
Thank you for inviting me to this colloquium and for giving me the opportunity to talk about combinatorial characterization of some finite algebraic varieties. This is a joint work with Fulvio Zuanni. In recent years, there has been an increasing interest in combinatorial characterization of algebraic varieties in finite projective space because important applications to practical topics such as few weight codes have made the field even more attractive. I want to introduce the principal subjects, finite geometries, linear codes with few weights, sets with few intersection numbers. A finite field has a prime power order. For any prime power order Q equal to P to H, there is a unique field of order Q, denoted by F sub Q. If H is equal 1, that is, if Q is a prime, then FQ is the ring of integers modulo Q, such as binary field, ternary field, and so on. The d-dimensional projective space PGDQ is obtained by taking a d+1 dimensional vector space capital V over FQ. Geometric objects are identified with subspaces of capital V. Points are one-dimensional vector subspaces. Lines are two-dimensional vector subspaces. Planes are three-dimensional vector subspace. Solids are four-dimensional vector subspaces. Properties of vector space dimension immediately give us familiar geometric properties of these objects. For example, in a d-dimensional projective geometry, 2 points lie in a unique line. 3 non-collinear points lie in a unique plane. The points and lines in a plane form a projective plane. An NK code C over FQ is a k-dimensional subspace of FQ to N. Vectors in C are called code words. The Hamming weight Wx of a vector x in FQ to N is the number of non-zero entries. A k for n, a k times n matrix G with entries in FQ is called a generator matrix of a linear code C if the rows of G are a basis of C. If we consider the dot product of two vectors of FQ to N, U and V, then the encoding of any vector X element of FQ to K is the code word C equal to XG. Denoted by Y1, Yn, elements of FQ to K, the columns of a generator matrix G of an NK code C over FQ. Then the code C is equal to the vectors with components xy1, xyn for any x element of FQ to K. Since the dimension of the code C is equal to K, the vectors y1, yn span the space FQ to K, the vector space FQ to K. If no two of the vectors y1, yn are dependent, then the code C is said to be projective. Let X an element, a non-zero element of FQ to K, denote by X_perp the subspace of the vectors orthogonal to X. Then the integer n minus the size of the intersection of X_perp with the set y1, yn is the weight of the code word xy1, xyn. Since for any x element of FQ to K, with the x different from 0, X_perp is an hyperplane of the projective space of dimension k-1 and order q. The sides of the intersection of the hyperplane X_perp with the set y1, yn is the intersection number of the n set y1, yn with the hyperplane X_perp. Therefore, we obtain all the non-zero weights of a projective NK code C over FQ by taking all the differences between n and the incidence numbers of the n set y1, yn. with respect to the hyperplanes of the projective space PG K-1Q. A code C is said to be a T-weight code if the number of non-zero different weights is equal to T. Thus, a projective NK code C over FQ is a T-weight code if and only if the n set y1, yn has T intersection numbers with respect to the hyperplanes of PG K-1Q. This connection makes possible the application of finite geometry to coding theory and conversely. Linear codes with few weights are important for its information to estimate the error correcting capability and the probability of error detection and correction with respect to some algorithms. Linear codes with few weights have applications in secret sharing, authentication codes, association schemes, date storage systems. From the geometrical point of view, sets with few intersection numbers in PGDQ are interesting objects. Classical algebraic varieties such as quadrics, Hermitian varieties, Bayer subgeometries are remarkable examples of few intersection sets in PGDQ. In his investigation on finite projective space, the Indian mathematician Rai Chandra Bose was the first in 1947 that used the purely combinatorial arguments in combination with geometry. Another Greek pioneer in finite geometry was Beniamino Segre. His celebrated result of 1954, stating that in the projective plane PG2Q, Q odd, every set of Q plus 1 points, no three of which are collinear, is a conic, was the first characterization of an algebraic variety in a finite space by purely combinatorial property. He provided the starting point of a new research direction in finite geometry. He indicated how certain algebraic varieties can be characterized by means of incidence properties. In 1955, Barlotti and Panella gave a characterization of elliptic quadric of PG3Q, Q odd, as sets of Q square plus 1 points, no three of which are collinear. In the same year, Tallini provided the characterization of quadrics in PGDQ for any dimension D and any odd order Q. In order to be a quadric, a given set of points must satisfy the condition of containing every line having more than 2 points in common with the set. In 1967, Hermitian varieties were characterized as point set of PGDQ square, meeting every line in 1, n, or Q square plus 1 points by Maria Scafati. All this characterization used intersection number with respect to lines. In 1982, De Finis and Resmini characterized Bayer subspaces as sets of PGDQ square, fixing the sides and the intersection numbers with respect to hyperplanes. But what is the problem of combinatorial characterization? An algebraic variety K can be thought as a set of points in a projective space that has a certain behavior with respect to subspaces. In a finite projective space PGDQ, the intersection varieties have a finite number of points. By combinatorial characterization of a variety, we mean the classification of those sets of PGDQ which, for axiom, possess a certain number of incidence properties of the given variety. The variety is intended to be characterized if one proves that a set satisfying the axiomatic properties is the variety, except at most some cases for particular values of Q, the so-called sporadic cases. The characterization will be a solid findings when the required axioms are few, essential, significant, and few also hard sporadic cases. In PGDQ, the projective space of dimension D and order Q, with the Q a prime power, let K denote a K set, a set of K points. For each integer I, such that I is greater than or equal to 0, less than or equal to Q to V plus Q to V minus 1 plus Q plus 1, let us denote by T sub I the number of subspaces of dimension V of PGDQ meeting K in exactly I points. The number T sub I are called the characters of K with respect to the subspaces of dimension V. a set K is said to be of class M1, M2, Ms with respect to dimension V if T sub I is different from 0 only if I belongs to the set M1, M2, Ms. Moreover, K is said to be of type M1, M2, Ms with respect to dimension V if T sub I is different from 0 if and only if I belongs to the set M1, M2, Ms. The integers M1, M2, Ms are called intersection numbers with respect to the subspaces of dimension V. Let us consider a symmetric square matrix, capital A, with entries in FQ. In PGDQ, a quadric is defined to be the set of points satisfying this equation. When Q is odd, QDQ is non-singular if the matrix A is non-singular. Ferri and Tallini in 1991 proved the following characterization of the parabolic quadric Q4Q. A set K of points in PGDQ with the dimension at least 4, the sides of K at least Q to 3 plus Q squared plus Q plus 1 of class 1 A, B with respect to planes, with respect to the dimension 2, with B greater than or equal to 2Q plus 1, and class C, C plus Q, C plus 2Q with respect to the dimension 3, with respect to the solids, with the characters T sub C and T sub C plus Q different from 0, is the non-singular quadric of PG4Q. This is a characterization with many conditions: the sides, the class with respect to the dimension 2, the class with respect to the dimension 3, and some other condition with respect to the characters. In 2008, Skilleworth provided the following characterization of the parabolic quadric Q4Q. A set K of points in PG4Q of class 1, Q plus 1, 2Q plus 1 respect to the dimension 2, and the class Q squared plus 1, Q squared plus Q plus 1, Q squared plus 2Q plus 1 with respect to the dimension 3 is a non-singular quadric of PG4Q. This is a characterization. This characterization improved the characterization of Ferri and Tallini because required the less condition than the characterization of Ferri and Tallini. Recently, I and Fulvio Zuanni have removed the solid incidence assumptions in the Skilleworth characterization of the parabolic quadric Q4Q and proved that a set K of points in PG4Q of class 1, Q plus 1, 2Q plus 1 with respect to the dimension 2 is either a parabolic quadric for Q, or an ovoidal cone, or the dual complete 11 cap of PG for 3. So we classify parabolic quadric with less condition than Skillworth. Now let's consider the involuntary automorphism of FQ square defined by X to Q and an Hermitian square matrix H with entries in FQ square. In PG DQ square, an Hermitian variety is defined to be the set of points satisfying this equation. When Q is odd, H DQ square is non-singular if the matrix H is non-singular. The definition is similar to quadrics, but used Hermitian matrix. Skillworth and Tass in 2009 proved the following characterization of non-singular Hermitian varieties H for Q square. A set K of points in PG for Q square of class Q square plus 1, Q to 3 plus 1, Q to 3 plus Q square plus 1 with respect to the dimension 2, and type Q to 5 plus Q square plus 1, Q to 5 plus Q to 3 plus Q square plus 1 with respect to dimension 3 is a non-singular Hermitian variety H for Q square. Recently, I and Fulvio Zuanni have removed the solid incidence assumption in the Skillworth and Tass characterization of non-singular Hermitian varieties H for Q square and proved that a set K of points in PG for Q square of class Q square plus 1, Q to 3 plus 1, Q to 3 plus Q square plus 1 with respect to planes, with respect to the dimension 2, is a non-singular Hermitian variety H for Q square, except for 3 possible small values of Q, 2, 3, 5, which can present sporadic cases. We would like to remove solid incidence assumptions in the characterization of subgeometries of PG for Q square and prove that the plane incidence assumptions are enough, except for possible few sporadic cases. This is the further work. Thank you for your attention.
Thank you so much, sir, for this enlightening session and sharing your knowledge with us. It's a pleasure having you, sir.
Thank you very much.
Now I would like to welcome our next speaker for the day, Dr. Pratima Rai. Dr. Pratima Rai is working as an assistant professor at Department of Mathematics, University of Delhi. Her area of specialization includes singular perturbation problems, differential equations, and numerical analysis. She has published various research articles in many reputed international journals. Today, she is going to speak on the topic singular perturbation problems and overview. I welcome you, ma'am. Are you here, ma'am? Okay. Yes, ma'am. Ma'am, are you able to unmute yourself?
Hi, can you hear me now?
Yeah, yes, ma'am. Sorry for the disturbance.
That's okay. So actually, I was seeing why I was not able to do that. Anyway, let me share my screen. So, is my screen visible?
Yes, ma'am.
Okay. So at the outset, let me thank the organizers for giving me an opportunity to talk at this event. So I have kept this talk very elementary. It is not any research work of mine, but this talk is just to give an idea about the area in which I am working, or many other people are working, and if someone is interested, they can also work on this area. So this talk is basically intended to give an idea about this area. So very elementary talk. Okay, so a brief outline of this talk is we will talk about what singular perturbation problems are. So how they are a special kind of differential equations and where they occur, some of the model problems. Then we will see what difficulties we have while we are going for numerical solution of such problems, and why standard numerical techniques, they are not applicable for these kind of problems, and we need to devise some special technique for such class of problems. So we will study some elementary technique on very basic problems. Then if I have time, I'll just classify SPP problems. Okay, so if I start with a problem, so consider a very simple initial value problem. So it's a first order initial value problem with some initial condition. Here there is a parameter epsilon. It's a constant parameter which lies in an interval 0 to 1. Okay, so if we see that this problem has this exact solution of this problem is given by this expression, we can easily find the exact solution of this problem. Now, in this problem, if I put this epsilon equals to 0, because if we can see this parameter epsilon is very small. So many a times what we tend to do is when we have any real world problem in which there are very small parameters, to simplify our models, we sometimes put these parameter equals to 0. Okay, so here epsilon is a parameter which is very small, but if I put this epsilon equals to 0 in this problem, what will happen? This problem will reduce to the problem ux equals to 0. And ux equals to 0 means the solution is trivial solution. And since the solution is completely determined, I know that it's a trivial solution, the problem cannot satisfy this initial condition until and unless this initial condition is 0. Okay, So it means, so I just cannot put, however small this parameter epsilon is, I cannot put this parameter epsilon to be 0. And if this parameter epsilon is very small, you can see that the solution of the problem somehow looks like this, that there is a very small region around 0 where the solution is changing abruptly, whereas away from this region, the solution is behaving smoothly. Okay, so I have borrowed this graph from this book. Okay, so now what we have seen a problem where there is a parameter, but if we are putting that parameter equals to 0, the reduced problem solution is not depicting the correct behavior of my original problem. So the problem, so in general, when we have models, the models which we get, in which we retain various parameters, that model we call as perturbed models. And the models in which we generally try to neglect the parameters, or we put the values of some of the small parameters to be 0, that model become reduced or the unperturbed model. And this region, which I called as boundary layer region, this region is basically, it's a region which adjoins the boundary or interior part of the domain where the solution dependent variable is changing very rapidly. Okay, so now consider another problem. It's a linear reaction diffusion problem. Again, in this problem, this parameter epsilon is there. If I put this parameter epsilon equals to 0, this problem will reduce to ux equals to 0. Now, this problem will not satisfy any of the boundary conditions given until unless both the boundary conditions are 0. So if we look at the exact solution of this problem, we will see that the exact solution of this problem is linear combination of these two functions. So, and if we see the graph, we see that there are thin layers, there are thin regions adjoining both the boundaries where solution is changing abruptly. We call these regions as boundary layer regions. And again, next problem is a convection diffusion problem. So in convection diffusion problem, we have this u dash term. Now here, if epsilon is 0, then the solution of the reduced problem will become u dash equals to 0. And whose solution will be some constant solution equals to u naught, because u naught was the first condition. Now this problem will again fails to satisfy one of the boundary condition. So in this problem, there is a boundary layer at one end. So now so basically singular perturbation problems are those problems in which there is some parameter epsilon multiplying the highest order derivative of the differential equation, and we cannot put that parameter epsilon to be equals to 0 because the solution of the reduced problems behaves very much different than the solution of the original problem. So study of this singular perturbation problems, it started in 20th century, in the beginning of 20th century. So, and it took birth at the Third International Congress of Mathematicians in Heidelberg. In that conference, Ludwig Prandtl, he delivered a talk on fluid motion with small friction. And he introduced the concept of boundary layers. So though Prandtl introduced the concept of boundary layers, but this area, it get popularity very late, around 1934, when Friedrich and Wassau worked, and then they called these type of problems as singular perturbation problems. So singular perturbation term was coined by Wassau and Friedrich. So basically, as you can see in the examples which I have considered, that the solution of the singularly perturbed problems, it consists of narrow subdomains where the solution is changing abruptly, whereas outside those subdomains, solution is behaving smoothly. So sometimes these layers can be at the interior point of the domain also. In that case, we call them as interior layers. Okay. So SPP problems, they arise in the modeling of various modern complicated processes, such as, let me just try to minimize this. Okay. So they arise in the modeling of various processes. I'm just naming a few, but there are various physical, chemical, and biological processes where these SPP problems occur. So some of the notable examples are fluid flow at high Reynolds number, financial model of option pricing, convective heat transport problems at large Peclet numbers, magnetohydrodynamic duct problems at high Hartmann numbers, simulation of oil extraction from underground reservoirs, drift diffusion equation of semiconductor modelings, and many more. And some model out of these, if I just give a brief idea about some of the model problems, I'll just consider 2-3 models. So Navier-Stokes equation steady state, it also becomes a SPP problem where at high Reynolds number. So it's a steady state Navier-Stokes equation. Here this R is known as Reynolds number, and this R is 1 by epsilon kind of term, because this at high Reynolds number, you can see that if R is 1 by epsilon, so considering the problem, epsilon will be multiplied by this. And if Reynolds number is very high, this epsilon will be very small. And this problem will become an SPP problem. Okay. And it's a very popular equation which occurs in the modeling of option pricing, Black-Scholes equation. So it's a, so we have considered a one-dimensional parabolic PD of this type. It's a Black-Scholes model. Here C generates the, so denotes the European call option. Sigma denotes the volatility. S denotes the current value of the underlying asset. T is the, small t is the time. Small r is the risk-free interest rate. Capital E denotes the exercise price. Capital T denotes the expiry time. So this problem also, it becomes a SPP problem when the volatility is very low. The sigma, if it is very low, it becomes an SPP problem. Okay, and this problem has several singularities, such as if you can see the boundary and initial conditions, this problem has several singularities. Our domain may be unbounded. The initial function, it may be piecewise smooth, so that there is discontinuity in the derivative. Okay, so, and another notable example is the problem of determination of expected time for the generation of action potentials in the nerve cells. So if we talk of the brain and we talk of neuronal activity, so generation of, so expected time for the generation of action potentials in the nerve cells by random synaptic inputs in the dendrites, that can also be modeled as an SPP problem. So this model was basically given by Stein. So Stein, he first gave a differential difference equation model, which incorporates the stochastic effect of neuronal excitation. So Stein assumed that in his model, he assumed that every excitatory impulse, it occurs randomly and it comes according to a Poisson process. And every event of excitation, it increases the depolarization put by some amount. We have called here by AE. And in the same way, there is an inhibitory impulse also, which arrives at the event time, and it occurs according to second Poisson process, and it decreases the depolarization by an amount I. So a neuron is fired whenever this polarization VR, it reaches a threshold value. And once a neuron is fired, after neuron firing, there is a refractive period, some T0, during which no impulses have no effect. Okay, and during this time, the depolarization potential is reset to 0. Then, when time becomes greater than T0, again, there is a unit depolarization. Now, we have considered the impulses according to the Wiener process. Then Stein later on said that if there are inputs which can also be modeled as we considered the Poisson process earlier. So if there are inputs which can also be modeled as Wiener process. So Wiener process is basically a real valued continuous time stochastic process. So it's a continuous process, whereas Poisson process is generally discrete. So we say if there are inputs which can be modeled as a Wiener process with the variance parameter sigma and a drift parameter mu, then we can have a differential difference equation given by this equation 2, where these two terms corresponds to the Poisson process and these two terms corresponds to the Wiener process. So it's a second order differential difference equation or we sometimes call it as delay differential equation because it takes into account the history of the system also. So this also becomes an SPP problem where this when this variance parameter is very low. Okay, so these are few of the notable examples of SPP problems. And now let's see what difficulties we have if we apply standard numerical methods. So I have considered very simple problems. So let me consider an initial value problem, which we first considered in this lecture. And let us apply a forward Euler scheme. So most of us study this scheme in undergraduate courses. Let's apply forward Euler scheme for its numerical solution. So forward Euler scheme will be given by this. Now, if I see the solution U1, first solution U1, so U1 will be given by the solution of this problem will be given by 1 minus h by epsilon, where h is the step size of my scheme. Okay, whereas the exact solution, exact solution at first step will be given by exponential of minus rho, so minus h by epsilon. So if I take h to be tending to 0, if the step size tends to 0, then the difference between the exact solution and numerical solution at the first point, it becomes exponential minus 1. This shows that this is not going to 0. It means that my numerical solution is not converging to the exact solution independent of this perturbation parameter epsilon. So the convergence is depending upon this parameter epsilon. So I have to choose my h in relation to epsilon in such a way, in some special way, so that I can get the convergence. So, but if rho is 1, it means if h is same as epsilon, we can see that we are not getting the convergence. So a natural question arises. Is it possible to construct numerical methods for such class of problems which works independently of the values of these perturbation parameters? So the answer is yes. So basically, two types of methods have been so basically I'm talking about finite difference schemes only in this lecture. So two type of methods have been constructed on the basis of finite difference schemes for the numerical solution of SPPs, and these are fitted operator methods and fitted mesh methods. So what is the idea behind the fitted operator method? In the fitted operator method, we take the mesh to be uniform, but somehow we are using some special discrete operator corresponding to our continuous operator to form the discrete problem. Okay, so this scheme was first given by Allen and Southwell for solving the problem of viscous fluid flow past a cylinder. Okay, so they replace the standard difference operator. For example, if I consider this problem, you can see that here it's a standard difference operator. We have used a forward difference operator here. But instead of this standard difference operator, if I use some specially designed operator which takes into account the layer behavior, then even if I take mesh to be uniform, I can get a scheme which gives me good solution irrespective of the value of the perturbation parameter epsilon. So that is the first approach. Now the second approach, fitted mesh approach. In this approach, what we do, we take the standard operators, but these standard operators are applied on mesh which are non-uniform. So here the mesh is constructed in such a way, or we can say the domain is discretized in such a way that there are large number of mesh points automatically in the layer region and less number of mesh points in the outer region. So the construction of the non-uniform mesh guarantees that there will be at least one mesh point. There are more than one, but at least there will be one mesh point in the layer region, howsoever small number of mesh points we take. So it means that layer behavior will be captured. So let's first see the fitted operator methods. So let me consider a very simple problem. So it's a linear convection diffusion problem, so that which we have already seen. For this problem, we are taking this fitted operator finite difference scheme. If you see, For U double dash, I have used a standard second order central differences scheme. It's a second order central differences scheme. And the first order derivative also I have used a central differences scheme. But you can see this term sigma. This term sigma is known as a fitting factor. So I said we use a specially designed operator. So we have changed our operator in such a way by introducing this sigma, such that even with very less number of mesh points, I can get very good solutions. This sigma here is given by this expression. So this sigma differs from problem to problem. It's not a particular sigma will work for every problem. So this sigma is known as fitting factor, and this fitting factor changes from problem to problem. So the question is now how we calculate this sigma. So the basis of calculating this sigma is the idea that we replace this problem. So we replace this discrete problem in which we have a variable coefficient by a problem in which we have a continuous coefficient, constant coefficient. And if I have all the coefficients to be constant, I can find its solution. So we find the solution of the discrete problem, or we can say it's now a difference equation, and I can use difference equation method to, we can solve the difference equation. So I can use that to find out the solution of this difference equation. And then for this same problem, which was the problem with this constant coefficient, I can find the exact solution also. And then ensuring the fact that at the mesh points, xi, so whatever mesh points I have, at the mesh points, this capital U, which was the solution of the discrete problem, which we get by replacing variable coefficient by constant coefficient, it should be same as the uxi. So giving this restriction, by putting this equality, I can find out the value of sigma. So you can see here in this case, the solution of the discrete problem is given by this, and solution of the continuous problem is given by this. And if I put uxi to be equals to small uxi, I can get sigma as this. Okay, so this is one scheme. So depending upon the problem, if I have a reaction diffusion problem, I may get some other sigma. If I have some other higher order problem, I may get some other sigma. But the idea is this, that we replace the given discrete problem with a problem with constant coefficient, and at the same time we replace our original problem also with problem with constant coefficient, and try to see that at least for the constant coefficient, the numerical solution and the exact solution should match at the mesh points. And then taking that idea, then we go and in our variable coefficient problem, we put that fitting factor sigma. Okay. So the next technique, which was fitted mesh technique, as I said, in that technique, we replace the standard finite difference operator. We take the standard finite difference operator, but we take specially designed non-uniform meshes. So this idea of non-uniform mesh was given by Bacalov in 1969. It was introduced by him, and those meshes are popular as Bacalov meshes, but it gained much popularity by Shishkin. When Shishkin in 1992, he introduced another class of piecewise uniform meshes, then this field of fitted mesh method gained a lot more popularity. Why? Because the Bacalov meshes were very complicated, they were difficult to analyze, they were difficult to create, where Shishkin meshes, they were very easy to construct and easy to analyze. Okay. So, and these were applicable to class of problem as compared to the Bacalov mesh. Okay. So if I talk of fitted mesh, you can see that I have considered that same problem, convection diffusion problem. This and the finite difference and the difference operator is a standard. It's a second order central difference. It's a first order forward difference. But xi, if you see the domain which was here, if you see here, the domain was uniform. The omega bar n was xi, where xi was given by I by n. So mesh was uniform. Here, the xi's are given by 2i sigma by n. So there is this sigma, it is known as transition parameter. So there is a transition parameter on which it depends upon how my domain is there. So if there is any layer, so sigma takes the value minimum to be 1 by 2 and 1 by epsilon log n. And what it do, it always, so if it divides the domain into, for example, 0 to sigma and sigma to 1, depending upon the location of the layer. If layer is at the left end, it divides the domain into 0 to sigma and sigma to 1 in such a way that it is guaranteed that in 0 to sigma also I have n by 2 mesh points, and in sigma to 1 also I have n by 2 mesh points. And if layer is on the right hand side, we divide the domain from 0 to 1 minus sigma and 1 minus sigma to 1. So basically sigma gives us the thickness of the bound layer region. Okay, so the meshes are standard, but the operators are standard, but the mesh is non-uniform. Okay, so now let's see a comparison between fitted operator and fitted mesh techniques. As both methods have their merits and demerits, we can see that fitted operator methods, they are very easy to apply because they work on non-uniform meshes. They work on uniform meshes. But as you can see, the way they are being constructed by assuming that replacing the coefficients by constant coefficient, we can see that they are not applicable to a very wide class of problems. So they are applicable to a very limited class of problems. Moreover, when we go on to higher dimensional problems, or I can say for solution of PDs, fitted operator methods are not that much applicable. But whenever they are applicable, they give better result than the fitted mesh methods. On the other hand, fitted mesh methods, they are easily extendable to higher dimension problems. They are easy to apply, but they have the complexity that because I'm dividing my domain into layer region and outer region, so I need to have a prior knowledge of the location and width of the layer. Okay, so that is the case. So I would have wanted to discuss about how we find location and width of the layer, but because the time is not permitting, so I will not go into how we calculate this. So the idea is, that there are two techniques. So they both have their merits and demerits, and how they can be constructed and how they can be extended to higher dimensional problems. So I'll just classify this SPP problems and tell you both classes of problem, what is the difference between. So SPP problems can be classified as turning point problems and non-turning point problems. So basically, when you talk of for example, if I consider this very simple second order boundary value problem, there is a coefficient AX adjoining the convection term. If this AX vanishes at some point in the domain or on the boundary of the domain, this class of problem becomes turning point problem. And if it has same sign throughout the domain, the problem are known as non-turning point problems. And turning point problems are more complicated than non-turning point problems because their solution depicts some very special features such as interior layers, twin boundary layers, and the resonance phenomena. Okay. And then there can be a simple turning point problem or multiple turning point problem also. Simple turning point problem means this solution AX is vanishing only at the one point in the domain. And there can be case where it is vanishing at multiple points in the domain, which may add to the complexity of the problem, and it may result in with many layers inside the domain. Okay. So as compared to the non-turning point problems, it is more challenging to find out the solution of turning point problems in case of SPPs. Okay, so these are few references which I have taken. So with this, I would like to thank you all for patient hearing. Thank you.
Thank you, ma'am, for this informative session. The talk was really insightful. Here we come to an end of International Colloquium on Recent Trends in Mathematical Sciences. Now we begin with valedictory session. I request Dr. Rashmi Verma to kindly deliver a vote of thanks.
Good evening, everyone. I hope I am audible to all.
Yes, ma'am.
Good evening, everyone. So it was really an enlightening discussions that we have been part of over the past 2 days. And we come to an end of 2-day International Colloquium on Recent Trend in mathematical sciences. The colloquium gave us deeper insights and better understanding of so many concepts and research trends in mathematical sciences. Considering the cross-disciplinary nature of the subjects and their applications in the real world, it is essential that we update ourselves about latest researches and concrete concepts in the disciplines, not just in mathematics, but in every other related areas like computer science, operational research, statistics, and even there are some applications in economics and other subjects as well. So as per our interest, we must keep ourselves abreast with it. So Professor S.N. Gupta discussed about statistical consulting and presented the real world applications that he had actually applied. He also suggested that every institution must have a consultancy cell for the practical applicability of statistics. Dr. Jagdish Chand Bansal enlightened us about computational intelligence, swarm intelligence, and their impact on our cognitive intelligence. It is interesting to note that these intelligence and artificial intelligence and their algorithms shall be playing much more wider roles and shall be affecting our cognitive abilities in near future and will definitely affect the future generations. The subjects, biology, coding theory, and statistics. If we listen to them, it sounds so different, but it was really nice to listen Professor Manish K. Gupta, who encompassed these widely different subjects together to discuss data storage, DNA computing, and DNA Gole subcodes and their applications to the real world. Professor Weston discussed briefly the conceptualization, comparison of nodes with further exploration of the machine learning for node theory. Dr. Phon Sriam enriched our knowledge about the least positive reduced residues, and it was interesting to hear about the very recent problems in number theory. Dr. Stefano Innamoratti highlighted the combinatorial characterization of some finite algebraic varieties in finite projective spaces. Dr. Mansaf Alam took us on an altogether journey of cloud computing technology. How much this technology has permeated our everyday life, the comparison of its increase every year. It was really interesting to note that Google, Zoom, and all these techniques that we are using today, they are being developed so much fast, and we really need a lot of research in these areas. Dr. Pratima Rai enriched our knowledge about singular perturbation problems, the difficulties in using standard numerical methods for SPSS, the unperturbed models, singularly perturbed problems, their importance, and definitely provided us with an opportunity to work in this area. I thank all the speakers for their gracious presence and enriching us with their knowledge. I would like to request Principal Ma'am to speak a few words. Principal Ma'am, is she there?
I don't think she's here, ma'am.
Okay. I think she must be busy somewhere because of all the other activities going on. I would like to thank our principal ma'am, Professor Harpreet Kaur, for her encouragement, guidance, and support at every step of the colloquium. It is her vision to take the college to the new heights and gave us all present all these recent trends so that research and other areas get the thrust that they require in today's times. Thanks to Dr. Lokesh Kumar Gupta, convener IQAC, for his invaluable suggestions and in the planning and execution of the colloquium. Thanks are due to the organizing committee of the Department of Mathematics, who has worked diligently in making this event a success. I would like to thank the technical team, Mrs. Sangeeta Pathak and her team, for her continuous support and technical help I would also like to express my thanks to the administrative staff, non-teaching staff, accounts department, Sanchar Manjeet Singh ji and his team for providing all the help required for the smooth execution of the colloquium. Definitely thanks to the student volunteers. It is really appreciated. They worked enthusiastically during the entire event from the conceptualization till the time it is happening. And I hope it would have been a good experience for them as well. And we thank the children for their help. Last but not the least, I thank you all the participants for their patient listening and making this event a grand success. Thank you all. Thanks, everyone. So I think you have shared the feedback form, and in case everyone has received the feedback form, in case any participants want to say anything, you can write it in the chat box or raise your hand. In case you want to suggest us anything or say anything about the colloquium, your suggestions are really welcome. You may raise your hand and we can make you a co-host and you can express. Yes, your certificates will be forwarded to you via email once we receive the feedback link for both the days. Kindly note that you have to fill the feedback and attendance form for both the days. Thank you everyone for the appreciation. I hope that our efforts were worthwhile and you really enriched with all the latest trends that we tried to encompass in this limited time of the colloquium.
Sangeeta, please, everybody can switch on their video for a group photo. Just allow everybody.
And maybe participants also.
Yeah,
yes,
participants.
including the
also.
participants.
Yeah.
And maybe in case someone wants to speak something, so we should welcome their suggestions also.
Yes, please, all of you can switch on your videos if possible.
May I share my feedback?
Karuna, you may share the feedback form for yesterday as well. Maybe somebody has missed.
Okay, ma'am.
But please write with it, it is for yesterday.
Okay.
So somebody has clicked the photo, Amin or Anshika?
Yes, ma'am.
Your certificates will be forwarded to you shortly. And in case of any problem, you can write it to us on the mail.
The picture.
We are done with the photo session?
Yes, ma'am.
Okay, then thank you all for joining us.